Okay, let's begin. So hopefully that quiz was fun. We'll be moving on. Yeah, at some point I'll probably do a little take one class and talk about proving stuff in general. But yeah, as I was mentioning in the quiz, one thing about proofs, you have to understand certain strategies that work. Like in general, if you're trying to prove a general claim, you can't give an example. Whereas if you're trying to disprove a general claim, usually you can give an example. So for example, I can make a declarative statement saying something like, all Jamaicans like heavy metal. I'm Jamaican, I didn't pick on you. Right? So I can make a statement like that, and you're saying, what do I have to prove or disprove this statement? Right? Could you actually prove that this statement is true by finding one Jamaican who likes heavy metal?
No.
No, right? Because the claim is every single one of them, right? It's not good enough to show me an example. Oh, here's this guy, Jhevon's Jamaican, Jhevon likes heavy metal. Did you prove the statement that every Jamaican likes it? No, right? But you can disprove the statement by giving one example, right? Here's Jhevon, he does not like heavy metal. Then obviously the statement is false. By giving you one example, I've proven that not all Jamaicans like heavy metal. So you have to sort of know when given an example would be a strategy versus having to prove something in general. So that actually came up in the quiz where I said, you know, A and B were general matrices. A has a row of zeros, right? It could be any size or whatever, as long as you can multiply them. Will it always be the case that the product has a row of zeros? You can't just show me one example of a pair of A and B where the row of A is zeros and the result is, there it is. There's an infinite number of different pairs of matrices that you could multiply, right? That's not good enough to give an example. It would be good if you can give an example showing it's not true. So, by the way, just before we move on, let's just get a feel of what people did. So I know that A has a row of zeros. I believe in one version I talked about columns of B's with zeros, whatever. So I know A has rows of zeros. Does the product have to have a row of zeros? What did you guys think?
Yes.
Yes.
What was your reason? Tell me your idea.
You can, the multiplication of the matrices are linear combination of A and B. Like each element of A, you multiply that with columns of B. So do you understand what I mean? So let's say ith element of A has the row of zeros, then you multiply A
You have
and
to
B.
talk about the row in general. You have to say the ith row of A, right? So you pretend that the ith row of A,
Let's
whatever
say
that
ith
I
row
is,
of
A has a row of zeros, then
has
what?
row of zeros.
Mhm.
Then AB is zero linear combination of zeros with columns of B.
Yeah.
So 0 times first column of B plus 0 times first column of, second column of B.
Yeah, you
So
could. Yeah,
that-
that's sort of the reasoning that I would put.
Yeah.
I'd write this up more specifically, but that's basically the idea. If I think of A and I write that as rows, right? Which remember one notation was this guy, right? All the way up to I don't know how many rows it could be n, right? This is proving in general because I'm not talking about a specific n can be whatever size you want. And then I look at B as a list of columns, right? So B1, B2, so on and so forth up to Bn, right? Then if one of these guys, let's say for example this one, I'd say the ith row, AI, is just a zero vector, right? Then if I dot product that with each column, I'm going to end up with zeros. And we already talked about multiplication last time, how the rows of A gives you the rows of the result, where you're dot producting each row with each column, right? So you times this by this, you are going to get, it's going to be a general form that I'm going to introduce now. So let's say the ith row would be the AI dot product with B1, and then you'd have AI dot product with B2, right? And then all the way down you have AI dot product with AN, AI dot product with BN, or whatever, right? But since your A is always the 0 vector, each of these guys are going to return a value 0, right? So you'll always end up with a row of 0. That's basically the idea. I'll write it up. When I put the solutions online, you'll see more specifically how to write that down. But that's the idea. And notice that I did things in general. My n can be any length. This can be any length. It's something I'm showing in general. I didn't give you one example, right? You know, okay, well, if this times that, I get a row of 0, therefore I've proven that you'll always have a row. That's not good enough. You give me one specific example if it's not good enough. And what if B had a row of 0s? Right, so I also asked a follow-up question. What if it was the other way? What if I knew that B had a row of 0s? Would I have to have a row of 0s in the result? No, right? And for that one, I could use a simple example, right? Because once it doesn't work for 1, it's not going to work for anyone. So I have, let's say this 3 and 1, whatever. And then this is 0 and 0. Then what would the result be? The first entry here would be 3. The entry here would be 4. Entry here would be 6. Entry here would be 8, right? So I can categorically say it's not true if B has a row of 0s that the result has to have a row of 0s. And it's good enough to show an example, right? But the other way around, it wasn't good enough to show an example. Anyway, we are moving on. We are continuing with section 1.3. We didn't finish that last time. We're going to finish it today, and so the homework for this will be due the next time. Tomorrow's a Friday. Yes.
I was going to ask if you could make it due on Monday for the late book people. We're still waiting for the book to come in. Is that possible?
There's no class on Monday. That'll be too long. Yeah, I'll probably get the questions for you guys and send them. Someone email me and remind me. I'll probably scan the problems from my textbook and email it to you guys or something like that. Yeah, so we're going to continue with this. This is matrices and matrix operations. So we talked about multiplication last time and what it meant, composition of functions, basically, yada, yada, yada. Now I'm going to give you a sort of general formula that you can do. Call for a matrix AI equals the ith row. For a matrix B equals the j column. Some textbooks use this notation, but it's not a general notation. I wouldn't assume that every single textbook would use this notation, but it's what I'm using. So let's actually be able to write this down. Now, assuming A is conformable to B, right? What does conformable mean?
A has the same number of rows as B has columns.
No.
Anything counts get rows.
Right, it's the same, it's the other way around. The number of columns of A is equal to the number of rows of B. Okay, so A is conformal to B, then the matrix AB is, by definition, how you're going to write it. Remember, the first row of A is the the first row of A determines the first row of the result. So you're going to have, let me sort of put some sizes to these first. So then if A is an m by n matrix and B is a, what size matrix would B have to have?
N by N.
N by R.
N by something else, right? The other part doesn't matter. N by P, N by R matrix. Then the matrix AB, how we think of it is the first row of the result comes from the first row of A. So at any given point, you're always multiplying the first thing dot product with the first column, gives you that number. The second number in the second slot would be the first row of A dot product with the second column, right? This pattern will repeat all the way down. You'd have the first row of A dot product with how many columns is in B? P, right? So this is dot product with B, BP, not there. And then this will be a similar pattern continue. The second row of A dot product with the first column would go in this spot. The second row of A dot product with the second column would go in that spot. Up to the second row of A dot product with the last column. This pattern continues until finally we have the m row of A dot product with the first column, the nth row of A dot product with the second column. The pattern continues up until the n row of A dot product with the last column. So one thing you notice, the first row of A gives you the first row of the result. The second row of A gives you the second row of the result, right? The rows are connected to the A matrix. Whereas in the first column, you always have the first column of B. The second column always has the second column of B, and so on and so forth. So B kind of controls the columns, A sort of controls the rows, which sort of answers the question on the other version of the quiz, right? If B had a column of zeros, right, then clearly, if, for example, B1 was the column of zeros, this whole column here would be 0, right? If A1 had a row of zeros, this whole row would be 0, right? So that's sort of giving you an idea of what the proof would look like. The columns depend on the B, the rows depend on the A. And that formula sort of comes from what the composition would look like, just following the pattern from the composition. So that's like a general form of multiplication. I think we actually did a few examples of those already, but that's the general formula that goes along with it. And now we are going to move on. I told you guys what a square matrix was already, right? Okay. So another definition. Suppose A is a square matrix. Let's call it n by n. Then it's sometimes called the main diagonal, but we can just say diagonal and you'll know I'm talking about the main diagonal. Then the main diagonal of A consists of the entries from the top left to bottom right. i.e. if A is a matrix A11, A12, all the way to A1n, all the way down to AN1, AN2, all the way down to ANN. This is A2, 2, etc. Then the entries on the main diagonal are these entries here. Those entries form what we call the main diagonal. A11, A22, A33, and are on the main diagonal. There's another definition. Going back to the bonus on the quiz, the trace of A, which is denoted by that notation, is the sum of the diagonal entries. I.e., by definition, trace of A is just equal to A11 plus A22 plus all the way up to ANN. Example, A equals 2, 3, 4. Then if I find the trace of A, it's just going to be 1 plus 4 equals 5. In this case, the trace of B is equal to 1 plus 2 plus 0 equals 3. So if I add all the entries on the diagonal, we call that the trace. Towards the end of the semester, we'll come back to the trace and we'll figure out some reasons why it's an important number to know. But for now, that's the definition. Some of the diagonal entries. What else? Note. Diagonal and trace are only defined for square matrices. So if your matrix is not square, it doesn't make sense for me to talk about the diagonal or the trace. That's something to note. Another definition. A diagonal matrix is a square matrix which has all non-diagonal elements equal to 0. This is called a diagonal matrix. If all numbers that are not on the main diagonal are 0, I say I have a diagonal matrix. Example. So in the first one, this is the main diagonal. Notice that if you're not on that line, you're 0. Right? Same thing here. This is the main diagonal. Notice that if you're not on that line, you're 0. Notice that it's possible to have 0 on the main diagonal, right? But it's not. What's important is the guys that are not on the main diagonal are 0. Same thing here. Look on the main diagonal. Everywhere else, you have zeros, right? It's okay for a 0 to be on the diagonal. That's fine. As long as everywhere else you have zeros, it's a diagonal matrix. Like a square 0 matrix is still a diagonal matrix. Right? Find the main diagonal, look everywhere else. Right? If it's zeros everywhere else, it's a diagonal matrix. Right? Diagonal matrices are really useful. Because they help us cut down on a lot of computation, right? And for example, later when we talk about things like determinants and inverses, we'll realize finding determinants, finding inverses, solving systems of equations, it's a hell of a lot easier when you're working with a diagonal matrix. And later on, almost towards the end of the chapter, when we talk about eigenvalues and eigenvectors, we'll realize that there are some matrices where it will be possible to transform them into a diagonal matrix and hence make computations involving those matrices a lot easier. And we'll actually show you exactly how to do that. So diagonal matrices, important because they simplify a lot of computation. And we'll talk about how to transform some matrices into them when we get to eigenvalues and eigenvectors. For now, we're moving on. There's a super important definition. This is a very useful matrix. It's called the identity matrix. The n by n with all ones on the main diagonal. Is called the and for her identity matrix. Notation is big I and a little subscript n. This is called an identity matrix. Very, very useful matrix, very important. Let's do some examples. For example, I2 is the 2 by 2 matrix that has all ones on the main diagonal. Since it's a diagonal matrix, it also has zeros everywhere else. I3 would be a 3 by 3 diagonal matrix where all diagonal elements are 1, and so on and so forth. So IN is in general like a 1, 0, 0, 0, 0, 1, 0, 0, 1. Where you have n rows. And of course, it's a square matrix, so you'll also have n columns. Right? This is called an identity matrix. What's nice about the identity matrix is it sort of functions as the multiplicative identity of the set of matrices. Right? So if I treated matrices as numbers, this guy would be the number 1. And notice he has many identities. He can look, it depends on what size of the matrix you're looking at. So the important property of the identity matrix is multiplication gives itself the matrix that you're multiplying by. Important property. If A is an n by m matrix, then if I take in times a, the result will be a. Right? That's why it's called the identity. Multiplication identifies who you're multiplying by. It does nothing essentially. And you can try this out. I'm not going to do it, but so that's multiplication on the left. Remember, multiplication is not commutative. If I put my I on the right side, what size I does it have to be to work? M. Right? Remember, when you're multiplying, the number of columns of the guy on the left must be the number of rows on the guy on the right. Right? The number of columns in A is m, so it must be equal to the number of rows here. If I look over here, the number of columns here must be equal to the number of rows there. That's why it's in on this side, it's im on that side. So an example.
Question before you raise that. What did you say about the last matrix?
This one?
Yes.
Oh, it's still a diagonal matrix. These are all examples of diagonal matrices.
Okay.
If zeros are on the diagonal, we don't care. The important thing is that zeros are everywhere else. That's what makes a diagonal matrix.
Okay.
Professor, can you not write so close to the edge of that board? It's really hard to see.
I don't know. Here?
Sure, that's better.
So if my A is something like 1, 2, 3, 4, 5, 6, then what size identity do I have to put here? Number of rows here is what? 3. Which means that how many columns I need here? 3. So it's going to be 1, 2, 3. Now if I take this times that, you can actually check for yourself. It actually gives you this guy back. And if this guy is on the left, 1, 2, 3, 4, 5, 6, multiply the identity on the right, what size does this have to be? Well, number of columns here is 2, which means that the number of rows there would be 2. So it's 1, 2. If you multiply by that guy, it actually gives you the same matrix back. Details left to the reader. What else do I want to tell you? Tell you about the identity matrix. I want to talk about what we call a linear combination. Another very important idea, and you'll see just how much later on as well. Suppose A1, A2, A3, to AN are n by n matrices, and C1, C2, up to Cn are scalars. Remember, our scalars are elements of a field. Then the expression C1 times A1 plus C2 times A2 plus all the way up to Cn times An is called a linear combination. So that's called a linear combination. You add them all up, multiply each guy by a scalar, we create what's called a linear combination. Very important idea. Later on you'll see how is also the case for, and I'll put in quotations, vectors. Because it's not, your mama's kind of vectors. It's a, we're going to define vectors in general later on when we talk about vector spaces. But in general, if v1, v2, all the way up to vn are vectors, then c1, v1 plus c2, v2 is a linear combination. Those of you fortunate to have taken differential equations before this class, you'll realize that solutions to differential equations normally have this form, where your vectors are like the functions in your solution, right? And your solution is always as a linear combination of functions. It's because of linear algebra that's happening in the background. And we'll study a lot more about why this idea is important and what it means. And I might talk about things like the Wronski and things like that as well. Okay, linear combination. What other definitions? I defined the trace already.
About the transpose?
Yes, the transposes is what the next definition in fact. Definition. Let A be by n matrix. The transpose of A, or you might see me refer to it as just A transpose, or you might put a D here. Denoted, the notation for that is A with a big T in the power. That's called the transpose of A. Is the matrix obtained by switching the rows and columns of A. First row becomes first column, second row becomes second column, etc. Some examples. Okay, remember how I spoke about earlier about being specific and things like that? See, little things like this are things you should notice, right? I didn't write n by n, I wrote n by m, right? This is kind of the nuances I want you guys to get used to paying attention to, reading very, very carefully. Okay, so it doesn't have to be a square matrix, it can be any size matrix that we can do this with. And things like that are really important. So 1, 2, 3, 4. A transpose of B. transpose of this is, what's the first row? Right, the first row becomes the first column, and so on and so forth. So my first row will be 1, 3, and my second row, 2, 4. Just that my first row becomes the first column, the second row becomes the second column, and vice versa. Just switching rows and columns. This one, first column, 1, 2, 3. Second column, 4, 5, 6. That's a transpose. What about this one? First column, 1, 0, 0, which is exactly the first row. Second column, 0, 1, 0. Third column, exactly. In general, identity matrix, you transpose it, what do you get?
Identity.
Itself. Try to write a proof for that. It's a stupid proof, but try to learn how to explain these ideas. What about this one?
Is a column matrix?
You write it as a column matrix. It switches this way. It's called transpose. We'll find uses for that later as well. In chapter 1, especially the first 2 sections, we're dealing with a lot of definitions. We need to define the language we'll be using later on.
Wait, did you say that we're defining a lambda?
Language.
Oh, language.
Because later on I'm going to talk, oh yeah, you take transpose this and you do that and blah, blah, blah. I'm just going to be talking about this like we're talking normal English, and you're supposed to be able to understand what I'm saying and follow. So that's a lot of what we're doing now. So that was a transpose. What else did I want to tell you about? Well, this leads nicely into section 1.1, so I'll talk about it. Or maybe I can just do it as a part of section 1.1. So consider section 1.3 done. We're sort of moving on to section 1.1. I'm going to talk about systems of linear equations and matrices. Okay. So let's define a linear system. A linear system of equations is a set of equations to form. So what do we call a linear system of equations? No. Equations, right? Matrix. I can use a matrix to represent them, but they aren't them technically. Something that looks like this: a11 x1 plus a12 x2 plus a1n xn equals b1. That is one linear equation in this system. That's the first linear equation. I'm going to use very suggestive notation. a21 x1 plus a22 x2 all the way down to a2n xn equals b2. This pattern sort of simplifies, continues, end up with a m1 x1 plus a m2 x2 plus, to be consistent, let's just write, it makes no difference, but write this n as an m. And write this m as an n. Up to a and n xn equals Bn. So this set of equations is called a linear system of equations. The Aij are scalars. The x, xp are variables. No, this is the same as, if I wanted to, I could write these things as a matrix, right? I have A11 x1 all the way down to A1n xn all the way down to AN1 x1 all the way across to ANN xn. This is B1, B2, all the way down to Bn. Right? By what we talked about the equalities of matrices, that would be the same, right? The first entry here is equal to the first entry there, which gives me the first equation, right? The second entry here would be equal to the second entry there. That's actually the second equation, right? All the way down to the last equation here equals the last entry there, would actually give me the last equation. So that's the same. I can throw both sides into a huge matrix. This follows by what we know about the equality of matrices.
I have a question about the notation of Bm. At the ends, those represent the rows
Columns.
and the columns. Okay.
It's always row by column.
Okay.
We talked about that in first or second class, I think. We know about equality of matrices. Right, so the first subscript is always the row. We always think of things as row by column.
Professor,
Yes,
what was the reason why you changed the subscripts again?
because I want to say n by m, which is what I usually say.
Okay, so is it BM or BN?
This is a bm.
That's the row.
This is n. That's right. What bm was what I was writing before, but I changed it. Also, by what we know about matrix multiplication, you'll know that this is often true. What we know about matrix multiplication this is the same as writing the following. I can actually break the left side down into a product of matrices. A11, A12, all the way down to A1n, A21, A22, all the way down to A2n, moving down, AN1, AN2, all the way down to ANN. There I can write x1, x2, all the way down to xn. This should have been an no, that's actually right. A1, A2. Right? By rules of matrix multiplication, realize that if you multiply this by that, you take a dot product, which is just a combination of the products of corresponding entries, and you end up with this. This guy here is what we call the coefficient matrix. Right? Notice that it gives you the matrix of all the coefficients of your variables. This guy here is called the solution matrix. In the future, I give you a linear system, I'm going to actually say, find the solution. What I'm asking you to find is this vector. Right? This guy here, I don't know what it's called. I call it the answer column. I don't know if I'm the first one to be called that or the last, but I've never really seen a standard way to call that last vector. It's a column vector. Ever since I was a kid, I called it the answer column. So we'll call it the answer column. We often represent a system by writing this very common notation, AX equals B, where A is a matrix, it represents the coefficient matrix. X represents the solution vector. B represents the answers column. So for example, whenever I want to make a claim about linear systems in general, I might write this equation down. For the equation AX equals B, what you really should be imagining is this, a whole bunch of equations, right? That would be our shorthand for this guy. A is called the coefficient matrix, blah, blah, blah. Now for naming things, if A is an n by n matrix, then the system is called an n by n system. So in the future I said, suppose you have an n by m systems of equations. I mean the coefficient matrix is actually an n by n matrix. Right? Notice here, note, n would actually equal to the number of equations I have. That we're going to talk about later. N is equivalent to the number of unknowns or variables. Form, let's say I write this, A11, A12, all the way up to A1n, and down to AN1, AN2, all the way down to ANn. I can put a bar here, and put B1, B2, all the way down to Bn. That form is called an augmented matrix.
Is that a BM?
Come again?
Is that a BM?
Yeah. Matrix.
It should be n, I guess.
Yeah.
For rows, right?
That it's the number of rows. Yes. Augmented matrix for the system. We may also represent this by B or A. Sometimes you put broken lines here. It's all a matter of taste, A, B. If you want to write matrices as square brackets, you can write as AB, or a broken line, A. Just one example of writing these down, and then we can go. right B. Matrix form means I want you to write it as AX equals B. And B, augmented form. So here's my first system. 2x plus 3y plus 7z equals 5. X minus z equals 2. 3x plus y minus 3z equals 1. X1 plus x2 plus x3 plus x4 equals 1. 2x2 minus x4 is 0. 3x1 minus 2x3 plus 7x4 equals 7. A. What does the matrix form look like? Meaning I want to write this as a matrix here, the coefficient matrix times the solution vector times the equals the answer column. What would I write?
2, 3, 7.
Right, just read off the coefficients. 2, 3, 7. 1, 0, negative 1. Notice that if a variable is missing, you just consider it a coefficient 0, right? You can think of this as plus a 0y. And then the last one is 3, 1 minus 3. What I write here? X, Y, Z. Right? The same order in which I write the coefficients here is the same order in which I'm going to write those going down. Notice that this column here controls your X values, that controls your Y values, that controls your Z coefficients. Right? And you sort of take the transpose and you write that along here. And similarly, you'd have here 5, 2, 1. What's the augmented form? What would it look like?
2, 3, 7, 5.
Right. One big matrix, 2, 3, 7, 5. 1, 0, minus 1, 2, 3, 1, minus 3. We realize this is going to be the first main step into solving any system of equations in a systematic format in which I'll show you next time. But that's basically it. 2 is no surprise here. It's going to be essentially the same. And then here. Okay, row here. 1, 1, 1, 1.
0, 0, 0.
Last one.
Yes, sir.
This would be x1, x2, x3, x4. This would be, huh? 1, 0, 7. Similarly here, I'd copy this down. This goes here. This goes here. 3, 0, minus 2, 7. This would be 1, 0, 7. What size system is this? This is a 3 by 3 system. So if I say we have a 3 by 3 system of equations, I mean I have equations sort of this size. This is a what?
3 by 4.
This is a 3 by 4 system of equations. The size of a system will tell us a lot of information. We can know, for example, how many solutions there are, if any solutions can exist, if they're unique solutions, as well as there are other things that we'll need for that. But we'll talk about that next time, solving systems. So 1.3 we actually completed, 1.2 not quite done yet, but we're almost done. We didn't actually did a lot of stuff in 1.1. So next class we'll probably finish 1.1 and 1.2. Stop there for now.